All right, so today we're going to talk about two things. One thing is experimental probability, and then the other one is the adding probabilities. So, experimental probability is when you use the results from an experiment to figure out the probability. So, you can estimate the probability of an event by using data or an experiment. And that is called experimental or empirical probability. And I think experimental probability might be a little bit easier than theoretical probability. Like you don't have to figure out the chances or the theory of how it would happen. You just use the results from the experiment. And it's going to be equal to the number of favorable outcomes over the total number of outcomes. All right, so this bar graph shows the results of tossing an oddly shaped number cube 100 times. So you can kind of tell, I don't know if on your paper you can tell, it's got weird angles on it. One thing to keep in mind is on the EOC, they're not going to call number cubes dice, they'll call it six-sided number cubes. So anytime you see six-sided number cubes talking about rolling a die. So this one is weird shaped, and so it was tossed 100 times, and you can see how many of each number it landed on. So what would you say for this number one? How many? This one's actually 17. What about 2? 21. 3. 16. 4. 11. Good. 5. 23. And then 6 is going to be 12. So I had to go through that and just make sure all that added up to equal 100 because sometimes it's hard to tell 17 from 16. Anyway, those are the results. And so number one, we're going to use those results to find the probability of rolling a 3. So you can tell that the shape of it is affecting how often it lands on different numbers. So if this was 100 times on a fair shaped like a regular shaped die, it would be more even. So you're less likely to get a 4 or a 6 on this one. All right, so the probability of getting a 3 is going to be the number of times it landed on a 3, which is 16, over the total number of times it was rolled, which is 100. And then that can reduce down to 4 over 25. All right. Now, a lot of these problems, they test your knowledge of other things besides just probability. So you need to know what a perfect square is and how many perfect squares there are in this list of numbers. So what are the perfect squares in this list? Should be 1 and 4. All right, so if I just added the number of times it landed on 1 or 4, that's going to be 28 out of 100 rolls, which is going to reduce down to 7/25. All right. Number 3 is a good practice. This is something we learned on the very first day of probability that I don't think we talked about on Wednesday. But we want the probability of not getting a 5. So if you remember, not is that little curvy thing. And it's going to be 1 minus the probability of getting a 5. And if we look at our results, there were 23 times out of 100 that it landed on 5, which is going to make the probability 77 out of 100. All right. And then this last one, we want the probability of an even. Okay. So a normal die, the probability of an even is just going to be 1/2. But this one is different. We would just add 21, 11, and 12. And that's going to be 44 out of 100, or 11 out of 25. All right. So what questions do you guys have on experimental probability? It's not too bad. Okay. So on Wednesday, which seems like it was a long time ago, we talked about when you wanted to find the probability of, like, you roll a die and you draw a card, you want the probability of getting a 2 and getting a diamond or whatever. Do you guys remember what we did with the probabilities when it was and? It's been a while. If it's and, you multiply the probabilities. Today, these problems are going to have or. And when it's or, you're going to add the probabilities. So we have 2 different types of events today. We have mutually exclusive events and inclusive events. And mutually exclusive events cannot occur at the same time. So that's like if you wanted to find the probability of rolling a 2 or a 5, you can't roll a 2 and a 5. So that's considered mutually exclusive. And then inclusive events can occur at the same time. Right, and then that would be like the probability of rolling a 2 or an even. You can get a 2 and an even, so they can occur at the same time. So on both of these types, when it's or, you're going to add, but sometimes you also have to subtract. So if it's mutually exclusive, where they cannot occur at the same time, all you're going to do, if you want to find the probability of A or B, is just add the probabilities. The probability of A plus the probability of B. And if they're inclusive, like if they can occur at the same time, you're going to add, so the probability of A plus the probability of B. But because A and B can happen at the same time, some of those things were counted twice. So what you have to do is subtract the probability of A and B occurring. And we'll do several examples of these. I think you're going to be okay. So just try to remember that or means you add the probabilities. All right, so let's look at number 5. So number 5 says each student casts 1 vote for senior class president. Of the students, 25% voted for Hunt, 20% voted for Klein, 55% voted for Vila. The student or a student from the senior class is selected at random. What is the probability that student voted for Klein or Vila? So can someone vote for 2 people? No. So this one is exclusive. They only get 1 vote. All right, so if we want the probability of Klein, which will do K, or Vila, we're just going to add those two probabilities together. Oops, that should be a V, sorry. Now, probabilities can be percentages. I know, like, we almost always have done just fractions, but we're just going to let this be percentages. So the probability that a person voted for Klein is 20%. And then that probability that the person voted for Vila is 55%. So the probability that someone voted for one or the other is 75%. All right. Now, if you're not great with what's in a deck of cards, you might want to have this sheet today. I know there's at least one on your homework that you have to know what's in a deck of cards. But a card is drawn from a standard deck of 52. Find the probability of drawing a red, and I tell you the reds are the hearts and the diamonds, or a face card, which is a jack, king, or queen. So can you draw a card that's a red face card? Yes. So this one is going to be inclusive. So when it's inclusive, you're still going to add, but you also have to subtract. So we want red or a face. So it's going to be the probability of a red plus the probability of a face minus the probability of a red and a face. Now what I like to do on these is just go ahead and make 3 fractions. So a fraction plus a fraction minus a fraction. And because there's 52 cards in the deck, I'm going to put 52 on all of my denominators. Right. And then the numerators are just going to be how many red cards there are in the deck, how many face cards there are in the deck. So how many red cards are there in the deck? 26 red, 26 red, 26 black. Do you guys know how many face cards are in the deck? I wish I had this on my screen, but I don't. There's 12. So there's king, queen, and jack of all the different 4 colors or suits. Right, and then do you know how many red face cards there are? There's 6. So you might at some point find this sheet that shows you everything that's in a deck of cards. Okay, and so then you can just type that in the calculator. I'm going to trust that you know how to do that, and it reduces down to 8/13 is your probability. So we are going to skip number 7 about the spa and go to number 8 about the marbles. So number 8 says that a bag contains 25 marbles, 10 black, 13 red, and 2 blue. A marble is chosen from a bag at random. What is the probability of getting a red or a blue? So for this bag of marbles, can you get a red and a blue?
Yes.
Is there a marble that's red and blue? If we just draw one, can we get red and blue? No. Good. So this is exclusive. So all we have to do is add. We don't have to worry about subtracting. So we want the probability of a red, or I have to write out the whole word blue because black also starts with a B. So all we do is add the probability of a red plus the probability of a blue. What should my denominator be? 25, the total number of marbles in the bag. Good job. All right, so once you do that, the top is just going to be how many red there are. Okay. And how many blue. All right. So when you add that, it's 15/25, which I'm fine with that being your answer. A multiple choice test, though, more than likely it'll be reduced down to 3/5. All right. Any questions?
So what? It was 15, 25, so why couldn't you do 5?
Yeah, did I reduce 15/25? Reduces to 3/5. Because you just divide the top and bottom by 5. Okay, so the next one, like the probability part is the same. Like it's you just add and subtract. But getting all the number of people with all the different categories is it's kind of tough. So on this, all the rest of the questions, we have 5 years after 650 high school students graduated, 400 had a college degree, 310 were married, and half of the students with a college degree were married. Okay, so I know it tells you straight up that 400 students had a college degree. So how many didn't? 250. Good. Those you either have a college degree or you don't. So those two numbers should add up to equal the total number of students. Right? You're also either married or you're not married. And so 310 were married. So how many are not married? 340. That should equal to the total number. All right, now this is where it gets kind of weird. This is two situations. So these aren't going to add up to equal the total number of people. This is going to add to equal the number of people who have a college degree. All right, so it says that half of the students with a college degree were married. Good. So there's 400 with a college degree. Half of those are married, so that's 200. So how many are not married?
200.
The other half. Good. All right. And then no college degree and married.
250. No.
There are this many that are married, and this many have a college degree. Oh, wait, hold on. Yes, this many are married, this many have a college degree. So how many don't have a college degree? This and this need to add equal 110. Good. All right. And then what about this last one? I heard someone say 140. So these two need to add to equal the number of people with no college degree. Good. So that's tough. I mean, that's a lot of like just reading through and figuring out what we're talking about. Once you do that, the rest of it is hopefully going to seem a lot easier. Okay, so all of these last ones are going to be inclusive because you can have both of those things. You can have a college degree and be married. So we want the probability that a student has a college degree. So we'll put C for college or M for married. Because they can have both, we're going to do the probability of college plus the probability of marriage minus the probability of both college and marriage. That says C and M, that very last one, for college and marriage. So what do you guys think should be on the bottom?
Wouldn't we zero them?
What?
If you did it that way?
Nope.
Because it's college plus married, then you're minusing both of those.
Nope. You're minusing how many have both. This is how many people went to college. This is how many people were married. Okay. You're basically subtracting away the ones that were counted for college and counted for marriage. So what should go on the denominator? Good. Total number 50, which is 650. All right. So Once we do that, then we're just going to look over here at these numbers. So for college, we look at college, so that's going to be 400. All right, we want them married, that's going to be 310. And then we're going to subtract the number of people who are counted in both columns, which is college and married, which is 200. All right, then we add and subtract, and that should reduce down to 51 over 65. All right, y'all okay? All right, we're gonna do a couple more. They're basically the same. Like once we do those blanks, the rest of it is pretty much the same. So this time, number 10, inclusive. 10 through 12 are all going to be inclusive. All right, so 11, we want the probability of a college degree or not married.
So if it's 510, you just put the first two numbers.
Say it again.
It's like the last one is 510, so you just put the two numbers.
It's 510 over 650. Yeah, so like the zero cancels out. Basically, it's like.
Okay. Like, is it gonna be kind of long though if we do?
If you do 510 over 650, no, I won't count it wrong. But if it was, bless you, if it's multiple choice, it probably will be reduced, but your calculator can reduce it. I can show you how if you don't know. All right. So I wish I would have just worded. I would have worded this different and just said single instead of not married. That's okay. So we're going to do the probability of a college plus the probability of not married minus the probability of college and not married. And I know all those denominators are going to be 650 because there's 650 people in this thing. All right, so college is 400. Not married is 340. College and not married is 200. And then if you just want to add and subtract the numerators and put it over 650, that's fine. If you want to write it in reduced form, that's also fine. It's 54 over 65. You want to try one on your own? Okay, just try it. You guys try to set up number 12 on your own. So it's the probability that a student does not have a college degree or is married. So probability of not college or is married. All right. You can give this answer several ways. You can do 450 over 650. You can do 45 over 65. Or the most reduced is 9 over 13. What questions do you guys have?